Okay, in this example, we're going to look at the flow of an incompressible fluid in a pipe. We were told this is a microfluidic setup, so that all the dimensions are going to be small. And we're told that the fluid is liquid nitrogen, and we're given the density of that fluid. Right, so the density is 0.807 grams per milliliter. Okay, we're going to want to consider if we would need to convert that because we want it to be in kilograms per cubic meter. So we'll give that a consideration in a moment. We also are told P1. All right, so we're told the input pressure. All right, so that's our P1 here. Okay, so P1 is 12 times 10 to the third pascals, because it's kilopascals. Okay, we then have A1, the input area, as 2.8 times 10 to the negative 5 square meters. And we also have the input velocity, V1. Okay, and V1 is given as 4 millimeters per second, or 4 times 10 to the negative 3 meters per second. Okay, all right, and we need some other information to actually solve for what we're being asked here, which is the two things, the output velocity and the output pressure. But before we get there, let's look at what we have. We have the height difference, so H2 minus H1, okay? So I'm going to call that delta H and show that in the figure. Okay, so right here, this is our delta H. Okay, and delta H is 1.99 centimeters. Okay, so 1.99 times 10 to the negative 2 meters. And our last piece of information, finally, is A2, which is 8.2 times 10 to the negative 5 square meters. Okay, so back to density real fast to see if we need to convert that. So we have grams per milliliter. So we have 1,000 grams per kilogram, and we also have 1,000 milliliters per liter. However, there's not a liter is not the same as a cubic meter. In fact, there's 1,000 liters per cubic meter. So let's do convert density as our first step. So I'll say note density must be converted. Okay, and what is that going to look like? Okay, so we're going to have 0.807 grams per milliliter multiplied by 1,000 grams per kilogram. Oh, sorry about that. Per kilogram. And then multiplied by 1,000 milliliters per liter. So 1,000 milliliters per liter. Okay. So let's get this. Okay. So let's write this like so, milliliters per liter. All right. Okay, so I made an adjustment here. So my first conversion, I had it the reciprocal of it because I need to cancel out the grams. Okay, so let's go ahead and do that. So we cancel out the grams, milliliters cancel, then we make our final conversion here, which is liters to cubic meters, which cancels liters, so then we're left with kilograms per cubic meter. And so you can see that in terms of these thousands also cancel, so we only have a factor of 1,000 difference, all right? So it's a nice clean difference. So once we make that conversion, we find that the density is 807 kilograms per cubic meter. Okay, so now that we're converted to SI units, we can go ahead and set up our equations. Okay, so to solve, we're going to use continuity and Bernoulli. Okay, so what our two equations then look like are we have A1, I'll put them over here, A1 V1 equals A2 V2. That's continuity. And then we also have P1 plus rho G Y1 plus 1/2 rho V1 squared equals P2 plus rho G Y2. Move this over so we can see it. And our last term, 1/2 rho V2 squared. All right. So we're going to plug in what we know and then solve for our unknowns. Okay, so rearranging, let's plug in our known values. All right, so we have in continuity, we have both A1 and A2. All right, so we simply need to solve for V2. That's our only unknown. All right, so V2 is going to be A1 divided by A2 multiplied by V1. Okay, so that's going to be one of the things that we were asked to solve for, because we were asked to find what is the velocity and pressure at the output. Okay, so we actually can just finish this one off right away. So we'll go over to the calculator. All right, and I'm going to put in the values, which I'll write out here. All right, so A1 is 2.8 times 10 to the negative 5 square meters. All right, A2, which is the wider section, is 8.2 times 10 to the negative 5 square meters, and our initial velocity was 4 times 10 to the negative 3 meters per second. All right, so in fact we can see, right, in terms of simply putting this in the calculator, our orders of magnitude are going to cancel out there. So we're just going to get 2.8 divided by 8.2 and then multiplied by 4. Right, so we can really think of that, and also I'll tell you why, right? Because we're told that it was 4 millimeters per second. Well, so we know our value is going to be in millimeters per second, so I just left off the 10 to the negative 3, but I'll write it in the correct units here of 1.37. Okay, yeah, we're working at 3 sig figs, so 1.37 millimeters per second. All right, now let me first write it in meters per second. All right, which is the same as 1.37 millimeters per second. Okay. All right, looks good. So notice that the velocity is entirely dependent on the change in cross-sectional area. The change in height had no effect on velocity, and that's important to remember, that the change in height doesn't control velocity. However, velocity is relevant for finding the final pressure, because that final pressure, P2, is going to be affected by both the change in height, because we've lost hydrostatic pressure, and by the decrease in velocity. So in fact, we can see, or it's important to stop and consider, that the change in height, since we're going up, is causing a decrease in pressure. So if the pipe had remained the same diameter, then we would expect P2 to be less than P1. However, the decrease in velocity, the fact that V2 is smaller than V1, right? So V2 is smaller than V1. Well, that can increase pressure. It will increase pressure. So which is going to dominate, the increase in pressure from the decreased velocity or the decrease in pressure from going uphill? So let's see. All right. So moving on to our Bernoulli calculation, we'll think about what we want to solve for. So I'm going to write P1 over here. Now I'm going to immediately make an adjustment to the equation, because we already wrote it out, because I want to put I want to set up for delta y, which is going to be y2 minus y1. So that means I want to have on the right hand side of the equation both of the hydrostatic terms. Over on the left hand, I'll leave the velocity pressure term, so 1/2 rho V1 squared. Okay. Over on this side, I'm going to have P2, and then this is going to be rho G y2 minus y1. Okay. And that's our delta y. Okay. And it's positive. Okay. That's what I call delta H, in fact. There we go. And then our last term, our 1/2 rho V2 squared. And we now know what V2 is. Okay. So let's then solve for P2. So then P2 is going to equal P1 minus rho G delta H, right, because that's decreasing pressure, so the minus is to be expected. And then we're going to have plus 1/2 rho v1 squared minus v2 squared. All right, and v2 is smaller, so that term will remain positive. So, right, so we got a decrease and an increase to pressure. All right. So let's plug in our quantities here. So P1 we have as 12 times 10 to the 3 pascals. We're going to then actually use the density that we converted, 807 kilograms per cubic meter times 9.8 meters per second squared. We'll plug in our delta H, 1.99 times 10 to the negative 2 meters. Okay. All right, and I'm actually going to move this down to another line so I can get it all in one line. So let's get it right over here. All right, and now our third term, the velocity pressure term. So 1/2 multiplied by 807 kilograms per cubic meter. Then our change in velocity. So let's see, our initial velocity was 4, right? So 4 times 10 to the negative 3 meters per second squared minus 1.37 times 10 to the negative 3 meters per second squared. All right. So let's plug that all in, see what we get. All right, so 12 times 10 to the third, okay, minus 807 multiplied by 9.8 multiplied by 1.99 times 10 to the negative 2, and then add our third term. All right, so we'll have 0.5, so 1/2, times 807 again for the density, and then in parentheses our 2 squared velocities. So I'm just going to do it like this for extra 0. That's our 4 millimeters, and I'm going to square that. Okay, and then subtract this value here. This one, however, I'll just go ahead and multiply it times 10 to the negative 3. All right, times 10 to the negative 3. Okay, let's get the 10 in there. All right, and then I'm going to close that off, so I'll have to add extra parentheses in here. All right, so let's go ahead and insert a pair of parentheses right there, or a single parenthesis. Okay, and then I can square that. Okay, like so, squared, and then finally close off that last set of parentheses. Okay, all right. Oh, I had the wrong negative symbol in there. All right, I think I did that twice, so let's fix it over here too. All right, so this one times 10 to the negative 3 should also be this symbol. Okay. All right, looks good. All right, so I get 11.8 kilopascals. So we can see that really, quite interestingly, they almost balanced out. The increase in pressure from the slower velocity almost exactly balanced with the decrease in pressure from going uphill. But it ended up being that the pressure did in fact decrease. So in other words, the hydrostatic pressure was a bigger effect than the velocity pressure. Right? So this term here had a greater magnitude than this term. Okay, all right. And let me just do one final adjustment so you can see this last line. There we go. I just cut it off so that we can see all the parentheses. Okay. All right, and thank you.